Okay, so let's start with our internal structure thing. Now, okay, we will be, well, we are mainly interested in the influences of the internal structure, not the macroscopic, not the translational motion, let's say, of the molecule or the atom. So, I mean, we will be assuming that the particle, their translational motion can be treated by the Maxwell-Boltzmann law. So we will be assuming that basically V over n lambda cube should be much, much larger than 1. Well, this tells me that Qn, the partition function for n particles, we can write it as Q1 to the n divided by n factorial. And Q1 will be just sum over the single particle states of e to the power minus beta epsilon I. Now the epsilon, the total energy of the system, will be basically the translational energy plus the internal energy. And if you look at the wave function, the wave function of my system will also be some translational wave function and some internal wave function. So this sum over single particle states will be sum over translational states sum over the internal states of my particle of e to the power minus beta epsilon translational plus epsilon internal. This is sum over the translational states. Well, we will assume that, again, for simplicity, just the translational states are independent of the internal states. If there is no external potential, there won't be any coupling between the translational states and the internal states of e to the power minus beta epsilon translational times sum over the internal states of e to the power minus beta epsilon internal. Now the first sum we had already evaluated. It's nothing but the partition function of a point particle with no internal structure, and that is V over lambda cube times, let's say, f of t, where this f of t will be a sum over the internal states. Where we are assuming here that the internal states are independent of the volume. Well, that would make sense, except at certain extremes. Because if you have your molecule over here, there will be an internal state. By internal states, we mean the states of the electrons, which should be close to the molecule, and the states of the nuclei, etc., which is within the molecule. So if you have a huge volume, the internal states will not be influenced. But just keep in mind, for example, if you take the hydrogen atom, the orbitals of the hydrogen atom, they go as n squared. So eventually, the size of the hydrogen atom becomes infinitely large for n sufficiently large. Well, this will be basically an ionized system. So we are thinking here that we are not considering such systems. So we will be assumed that the temperature, let's say Kt, is much less than the ionization. So basically, if it's excited, the only excited states should be the ones close to the ground state. But you see, the excitation energy and ionization energy, they are not much different. What is the excitation or the ionization energy of atoms' typical values?
Goes like 1/4 of the ionization energy, right?
Yeah, I mean, they're of the same order of magnitude, let's say. How many kelvins do they correspond to?
How many kelvins? Maybe.
Well, keeping in mind some numbers would help to answer such questions like the room temperature.
Maybe 7,000.
This is typically 1/40 electron volts. Yeah, this room temperature is kind of easy to remember. It's something like 300 Kelvin. And 1/40 is quite a round number, so it's 1/40 electron volts. So 1 electron volt is typically 10 to the power 4 Kelvin. So the ionization energy or the excitation energies are typically 10 to the 4 Kelvin to 10 to the power 5 Kelvin. So if you are at these temperatures, there will be ionization. So you have to take that into account. But if you are lower than that 10 to the power 4, 10 to the power 5 kelvins, you can just ignore the ionization. And also, let's say, at room temperature, 1/40 electron volts, you are not exciting anything. You are not exciting the electrons. At least you are not creating any radial excitations, let's say, at room temperature. So you can just ignore them. You can just assume that all the electrons, at least their orbital wave function, is in the ground state. So that is one assumption we will be making. Now, we can discuss several cases, let's say monatomic systems. Now, in the monatomic systems, basically, let's say you are just want helium, nitrogen, neon, or just gas systems made up of one atom. Oh, before going that, by the way, let's say this is what we have Qn. Then we can look for. Okay, this is one thing we will assume, that the temperatures are much lower than the ionization energy, so that we are sure that within this limit at least f of t will be independent of volume, this sum, because the internal energies will be independent of the volume of the system. Now once we know, let's go back. This is Q1. Q1 to the n factorial Q1 to the n divided by n factorial. A, the Helmholtz free energy, if you remember, this is just minus kT times logarithm of Qn. This is minus kT times n logarithm of Q1. Q1 over n plus n. This is our Qn. Logarithm of Q1 over n plus n, or this is equal to minus ktn logarithm of v over lambda cube n plus n.
Isn't it plus 1?
This one? Oh, yes, this is plus 1. I took out the n. Plus logarithm of f of t. You see, the A is, again, separates. There's a contribution to Helmholtz free energy due to the translational motion. Plus A, there's a contribution due to the internal degrees of freedom. And this A internal degrees of freedom is minus n kt logarithm of f of t. Or let me switch to the notation of the book. This is nkt logarithm of j of t. And so we can express everything in terms of A. If you remember the thermodynamic relation, the A was equal to minus SDT minus PdV plus mu dN. Well, since we are looking at the internal degrees of freedom, there's no pressure due to the internal degrees of freedom. dA int would be just minus S int dt plus mu int dN. So we can write down the contribution to the entropy due to these internal degrees of freedom. This will be minus dA over dt, dA int by dt, which is nk logarithm of j plus nkt dj by derivative of the logarithm of j with respect to temperature. Energy of the system will be just A plus T times the internal energy, entropy, A int times T times S int. Well, this is minus nkt logarithm of j plus nkt logarithm of j plus nkt squared derivative of the logarithm of j with respect to temperature. So this is the energy. We can calculate the chemical potential, the contribution to the chemical potential due to the internal degrees of freedom. And if you look at this differential of A, the chemical potential is nothing but the derivative of A with respect to N. This is minus nk derivative of the logarithm of j with respect to t. N. Minus kt logarithm of j. So once we obtain this j, we know how it contributes to various thermodynamic properties. Now let's look at the monatomic gas. Okay, so we can consider various cases. Okay, so if you look at the energies, the wave function, the J, or the total energy, internal energy. Now, the internal energy of any system will be given by, let's say, the electronic, the contribution to the energy from the electrons, plus the nucleons, the nuclei, plus if there is any rotation of the system, rotation, plus if there is any vibration, plus vibrations. Well, these energies, they cannot always be separated in such a form. But just if you assume that there is such a separation, then the J, as a function of temperature, will be there will be a contribution due to the electronic degrees of freedom. There will be a contribution due to the nuclear degrees of freedom, another contribution due to the rotational degrees of freedom, and then the vibrational degrees of freedom. The J will be just the product of all of these. Just because, well, the reasoning is basically exactly like in this one. We separated the energy as the sum of the translational energy plus the internal energy. This separation causes the partition function to be separated into products. And J is nothing but the partition function due to the internal degrees of freedom. So if you separate the internal energy into various components, then the partition function is also separated into products of various components. Now, in the monatomic case, there is no rotation, there is no vibration. So there is no corresponding partition function. The only thing we have is the electronic and the nuclear structures. Now, if you look at the electronic energies, we can consider various cases. such as L is equal to 0, S is equal to 0 case. L is equal to 0, S is non-zero. L is non-zero, S is non-zero. Now I said the reason why we consider these different cases is that, well, let's look at the first case. L is equal to 0, S is equal to 0. Oh, sorry, we also have L non-zero, S is equal to 0. Well, if you remember again your quantum mechanics courses, there's the, if you look at a realistic atom, you have the spin-orbit couplings, which is a coupling between L and S, which leads to a fine structure in the spectrum. Then there's the spin-spin coupling of the electronic spin and the nuclear spin, which gives the hyperfine structure. Well, if the L and S they're both 0 to start with, there's no fine structure. So there's the ground state is non-degenerate. There's a single state. So the number of states the electrons can be in is just 1. Now, if L is 0 whereas S is non-zero, there's still the hyperfine interaction between the spin of the nuclei and the spin of the electrons. But you see that hyperfine structure is very small. Basically, the temperature corresponding to this hyperfine structure, this should be something like
5 Kelvin, 10 Kelvin.
1 Kelvin or even less. So, I mean, for typical temperatures, we can just ignore it. There's no hyperfine structure. So this will be, the electronic states can be in 2s plus 1 different states. Well, if S is 0 whereas L is non-zero, again, there's no separation. There's no, you see, the L doesn't, where different values of L will basically have the same energy. So again, the electronic degrees of freedom will have 2L plus 1 degenerate states. Now, if both of them are different from 0, then we have a spin-orbit coupling. And the temperature for spin-orbit coupling let me see, it should be something like 100 electron volts.
100 electron volts? Or 100 Kelvin?
100 Kelvin, sorry. Yeah, this should be something like 100 Kelvin. So we have to take that into account. Now, let's say in these ones, JE is just 1. It's just a constant. And in this one also, JE is just some constant. And this one also. Just a constant. There is also the nuclear partition function. It's already a constant. So you see, except in this case, the partition function due to the internal degrees of freedom will be just some constant. Well, let's go back. How do they change the thermodynamic properties? Well, there is just a constant added to the chemical potential. Energy, since we are looking at the derivative, is not modified. Internal energy is, you see, J is just a constant. There is no internal energy due to these degrees of freedom. Well, that's basically what we had assumed. We just said they are all degenerate. Let's fix that energy to 0. So that's why there is no contribution to the internal energy. Well, let me also write the specific heat, which is just Nk derivative with respect to T of T squared derivative of logarithm of J with respect to T. So there's no contribution to the energy, there is no contribution to the specific heat. Internal energy, there's no contribution. The entropy, well, you see there's a contribution to this term. J is just by just another constant. Now the interesting case would be the case when L and S, they are both non-zero. So the electronic J will be again sum over the microstates, internal microstates this time, of e to the power minus beta epsilon. Well, the energy will depend on the total J value only. So we can write this as sum over J, e to the power minus beta epsilon J. Well, the dependence on J is due to the rotational symmetry. If you have a rotational symmetric system, the energy can depend on J, but it cannot depend on Jz. Because the rotation just changes mixes different values of Jz, but rotation, since it commutes with the Hamiltonian, it shouldn't change the energy. But for a given J, there are 2J plus 1 states. So sum over all the microstates is just 2J plus 1 times that factor, summed over all possible J values of my system. Now we can look at various cases. Very high temperatures. So basically, if the energy splitting between different J values is much smaller than the thermal energy of the system, then basically we can just ignore that splitting. And that amounts to saying that if beta epsilon J is much, much less than 1, they're almost 0, so the electronic partition function is just sum over 2J plus 1. This is basically 1 exponent. And this is nothing but 2s plus 1 times 2l plus 1. It's again just a constant. So there's no contribution to the specific heat. The other limit is when Kt is much, much less than epsilon j. Well, this tells me that beta times epsilon j is much, much larger than 1 for all states. But of course, one of them will be much smaller than the other ones. So let epsilon 0 be the smallest one. Je is again this sum. But you see, this time, well, beta is huge because we are looking at the low temperature limit. So this beta epsilon j is much, much larger than 1. All these exponentials are very small, but the largest one is j is equal to j0 term. Now let's see, is there a contribution to the specific heat? So the reason why we are looking at the specific heat is it's easy to measure. So let's see what was the expression of the specific heat. This is our specific heat. Which is in this case nk, derivative with respect to t of t squared, derivative with respect to t of logarithm of 2j0 plus 1 minus epsilon, let's say epsilon 0 over kt. Well, the first term, this derivative is just 0. If you look at the second term, it's just 1 over t. If you take the derivative, it becomes 1 over t squared. If you multiply by t squared, it's just a constant. So there's a constant additive term to the energy, and it doesn't change the specific heat. Well, a constant term added to the energy makes sense, because since we are looking at the very low temperature limit, the system is basically in the ground state. And epsilon 0 is nothing but the energy of the ground state. So the total energy will be the translational energy plus the energy of the internal ground state. So there's a constant added to the internal energy. And hence there is no change in the specific heat. Now if you would plot the specific heat, well, of course there is a contribution to the specific heat due to the translational motion. Due to this electronic degrees of freedom, there is no contribution at small temperatures. And there is no contribution at large temperatures. Because we have seen that in small temperatures, just this derivative is 0. At large temperatures, J is just a constant, so there is no contribution. Of course, in between, there will be some contribution. So you would expect some structure in the specific heat at some intermediate temperatures, where this, let's say, let's call this T0, KT0 is equal to some epsilon J for some J at least. Because we had to consider two limits when KT was much smaller than all the epsilon J's and much larger than all the epsilon J's. There is no contribution to the specific heat. But at some intermediate value, there will be some contribution, because the electronic partition function is non-trivial, non-zero, in somewhere in between, so that we will still get the contribution. And well, since there is no rotation and no vibration, that's more or less it for the monatomic systems. Now let's look at diatomic systems. Well, let's leave this for next week. Probably there will be some lecture now. But the basic idea is essentially the same. Just identify the internal states. And once you identify the internal states, you have to also check whether the internal energy shifts or energy shifts due to the internal states. Are they larger than the temperature, smaller than the temperature, or at the same order of magnitude, because the behavior will be mainly different. And then you know what the contribution is. Eventually what we will be aiming at is so how the specific heat changes as a function of temperature. So you see, for example, if you can somehow, if you have a monatomic system, well, this is what the specific heat should be, and if you can actually measure the specific heats, you should see some structure in the specific heat, some deviation from 3nk/2, and the temperatures at which there is a significant deviation will tell you what are the internal excitation energies of my system. So you can determine the internal excitation energies. Due to, of course, here this is the spin-orbit coupling. Now, in the case of diatomic systems, we have there's the spin-orbit coupling. There will be some contribution from that one. There is plus contribution from the vibrational modes, and then from the rotational modes. And we will see that as the temperature crosses each one of these boundaries, there will be a jump in the specific heat. So at very low temperatures, there is no vibration, so vibrational modes will not contribute. But if the temperature is higher than the vibrational energies, then for each vibrational mode, you will get a contribution KT. At temperature much higher than those vibrational modes. And then you have this transition region, the transition from no contribution from vibrations to a contribution KT from the vibrations will be smooth. It's not just a jump. Questions? If you have realized, we are mainly repeating ourselves over and over again. At least from this point on, it will be more apparent. So the basic philosophy, let's say, of statistical physics is what we had already covered. So we have to take some sums over the microstates of our system. In the microcanonical ensemble, we are just summing 1 over all the available microstates consistent with our constraints of energy and the number of particles. In the canonical ensemble, we will be summing over the microstates of this Boltzmann factor e to power minus epsilon E over kT, consistent with the constraint of given number of particles. And in the grand canonical ensemble, basically, there is no constraint. And the next thing is you have to just identify what are the microstates and what does a summation over the microstates mean for your system. How can you express it in a more simple, more manageable form? So that's basically what we are doing over here. Up to this point, we had ignored the internal microstates, internal states of our particles. Now we are saying that, okay, the microstates of my system also contains the internal microstates of the particles. And then once we are done with this chapter, we will start. What about the fermions? What about the bosons? And basically we will be putting A is equal to +1, A is equal to -1 in our previous derivation. And then what are the consequences? And these consequences we will also derive just using thermodynamic relationships. So in that sense, our formalism is finished. Now what does this formalism tell us about various systems? Okay, so see you next week.